Hello, this is Tim Lichtenberg from Oxford and Sebastian Krijt from Exeter. In this talk, we will present the results of our research project on how the combined evolution of the chemistry and dynamics in the disk and geophysical processing on planetesimals may alter the abundances of carbon during planet formation. Why do we care about carbon? That is, because the story of life is essentially one of carbon and its many compounds. For instance, you yourself are about 20% carbon, and you may right now drink or eat carbon, and your workday may be rather limited without a sufficient and continuous supply of carbon in its many forms. On a global, more planetary level, carbon compounds, mostly in the form of CO2, control the surface temperature by regulating the climate of terrestrial worlds. As illustrated on the left, the carbonate-silicate cycle is thought to establish a long-term climate thermostat on planets with a mobile lid tectonic regime similar to the one on Earth. As shown on the bottom right, higher CO2 levels decrease the outgoing long-wave radiation, which heats the planet. Varying levels of carbon are therefore needed to balance different installation levels and sustain habitable surface conditions over stellar main sequence lifetimes and at different orbits, as shown on the top right here. This shows that carbon is essential for habitable worlds. Curiously, however, carbon is actually strongly depleted relative to the nominal values in the Sun or in the interstellar medium. The left plot here shows the amount of carbon relative to silicon in various extraterrestrial materials and planetary bodies relative to the Earth, which is depleted by several orders of magnitude. This can be compared to water as seen on the right. We as humans live on the surface of Earth, and our worldview is strongly biased toward our everyday experience. While, for instance, the global oceans make our own Earth appear to be like a water-rich planet, it is in fact very dry. The same is true for carbon. While it is crucial for climate and the basic chemical ingredients of life, too much of it would be destructive rather than positive for life. This strong carbon depletion can also be seen in meteorites. Here shown is carbon mass fraction versus C/N ratio in meteoritic materials. Carbon is most depleted in the Earth relative to all other meteoritic objects. This seems to suggest that carbon is depleted somehow during planet formation. But where does this trend start?
Hey everyone. Okay, let's start at the beginning. In the interstellar medium, you'll find roughly 1 carbon, oxygen, and nitrogen atom for every 10,000 hydrogen atoms. In cold molecular clouds, these elements are then distributed amongst different carriers, something like this. For example, roughly half of the carbon is in refractory compounds, which have high condensation temperatures, while a significant fraction of carbon and also oxygen is in carbon monoxide, which, with a condensation temperature of only 20 Kelvin, is highly volatile. If we imagine these raw materials are incorporated unaltered into a protoplanetary disk, we can compare the condensation behavior to the temperature and pressure found at different locations to predict what the composition of the solids, ices, and gas there will be. For example, imagine starting here close to the star and slowly walking out along the midplane. The decreasing pressure and temperature would result in things like water, carbon dioxide, and carbon monoxide to disappear from the gas and form ice, resulting in this step-like behavior for the C/O ratio, for example. This picture is very powerful in its simplicity, especially if you want to compare compositions of solids and gases to exoplanets, for example. But it assumes the disk to be static and that these molecular ratios are fixed. A hint that these assumptions may break down comes from looking at the so-called warm molecular layer. Here, above the disk midplane, the temperature never drops to very low values, and the decreased pressure results in many of the volatile molecules never being stable as ice. In this layer then, in a static picture, you would always expect to find a CO to H2 ratio of about 10 to the minus 4, as inherited from the ISM. However, there's mounting evidence that this is in fact not what happens in nearby disks. This fantastic plot by Coco Zhang and collaborators shows how the gas phase CO abundance in the warm molecular layer decreases by almost 2 orders of magnitude in about 3 million years. The data points here are in some cases individual disks, in other cases entire star-forming regions, and I urge you to read this letter if you want to know more. It's really great. Understanding the cause for this depletion is crucial, because first of all, these timescales are similar to planet formation timescales, and I mentioned already that CO represents a large reservoir of carbon and oxygen. But also, CO emission is often used as a tracer for total disk gas mass, a calculation that requires knowledge of the CO to H2 conversion factor, and therefore not grasping or not understanding the temporal evolution of this ratio can lead to complicated and age-dependent errors in our estimates of disk masses, which is a very fundamental parameter for planet formation theory. Last year, we published a study attempting to explain this CO depletion through numerical models. These models included local chemical processing, dust coagulation and the formation of pebble-sized particles, and gas and dust dynamics in the form of turbulent diffusion for gas phase species, and additional vertical settling and radial drift for pebbles. What we found was that a combination of ongoing chemical processing in the midplane and sequestration of CO ice on pebble-sized particles, which are effectively confined to the midplane, could just about deplete these surface regions by the observed 2 orders of magnitude on the relevant timescales. Additionally, in models in which CO-rich pebbles were allowed to migrate radially, we saw an elevated CO abundance just interior to the CO ice line. This plume of gas, enhanced in CO, has since been observed in at least one system. Crucially though, both processes contributing to the CO depletion require mixing and exchange of material between the surface layers and the disk midplane. And through this connection, the observed gas phase abundances in the surface layers, as seen for example by ALMA, then allow us to constrain the composition of the ices in the disk midplane available for planet formation. These models that I highlighted on the previous slide did not go beyond the formation of pebble-sized particles, but in the modern picture of planet formation, it is these pebbles that accumulate in certain disk regions, it's not completely clear where and when this happens, to form dense clumps that can collapse to form gravitationally bound planetesimals. In such a picture, the bulk composition of the primordial planetesimals is then set by the composition of the pebbles at the time and location where this accumulation occurs. For this new study with Tim then, we looked at the pebble compositions predicted by these disk models, which vary significantly with both time and location, and asked what would happen to planetesimals born with such compositions. Over to you, Tim.
In the solar system at least, early formed planetesimal bodies did not remain in their pristine state. The reason for this is shown here on the left. Radiogenic internal heating from aluminum-26 can drive substantial heating and thermal evolution of bodies. The heating is short-lived due to the 700,000-year half-life of aluminum-26, but it can be extreme. On the right, you see an illustration of the potentially strong magmatic activity that can develop on early formed bodies. Here, we see a video of a 3D simulation of a spherically symmetric, silicate-dominated planetesimal that melts and internally deforms due to the strong radiogenic heating. Color scales with temperature, and the planetesimal is heated from the inside out. This can have strong consequences on both the structure and volatile abundances of these bodies. The bottom part on the left illustrates how iron cores on planetesimals form due to radiogenic heating, and upper parts shows how initially volatile ice-rich planetesimals melt and degas their primitive volatile abundances that are inherited from the disk. Evidence from meteoritics suggests that this devolatilization process after planetesimal formation substantially shaped volatile abundances of the meteorites we measure today and the final bulk volatile abundances of the forming terrestrial planets. However, the initial abundances of aluminum-26 can vary by orders of magnitude across planetary systems, as shown in this plot to the left. The variation predicted by simulations of aluminum-26 enrichments in forming planetary systems suggests that the abundances at the time of planetesimal formation can vary strongly. The resulting heating rates in planetesimals correspond to 10 to the 2 to 10 to the 8 times the present-day internal heating rate of the Earth, which still drives the tectonic evolution of our planet today. This means extrasolar planetesimals can be heated to similar levels as solar system objects, or not at all. This may have profound influences on the volatile abundances of planetesimals formed in carbon-rich regions of the disk, as suggested by the rapid variation with time of CO abundances in ALMA disks. In our project, we therefore explored how the evolution of the material composition in the disk plus the processing on planetesimals evolves with time and for different initial conditions of the planet-forming system. On the left, you see the starting conditions of the disk system. The volatile to rock ratio varies radially. We focus on the region that can be probed with current disk observations, which is dominated by the evolution of the CO content. The next step in our model is the time evolution of the disk, where the composition of the dust grains evolves due to dust coagulation, settling, radial drift, and chemistry. At some point, planetesimals are formed, which is a free parameter on our model. In this case, it is at 2 megayear after system formation. At this time, the composition of the dust is inherited by the planetesimal, whose composition then evolves according to the loss rates predicted from planetesimal degassing, which is a function of the planetesimal size and the heating rate from radioactive decay. On the bottom right, you see a parameter map of the heating of planetesimals as a function of the enrichment level of the planetary system, from a solar-like enrichment level to 1 magnitude below. Possible volatile loss in planetesimals is compared to the maximum temperatures reached. According to degassing experiments in chondritic meteorites, CO, H2O, and CO2 feature different outgassing temperatures, where CO2 is lost first, followed by H2O and then CO. In the bottom left, nearly all is retained. In the top right, nearly all is lost, but the time of loss can vary strongly depending on heating rate. The combined evolution shown in the bottom left illustrates that across the disk, the abundances in all volatiles sharply decrease, but at different levels that generally are a function of the heliocentric distance, timing of planetesimal formation, and internal processing. On the next plot, we compare different heating rates, which are displayed by different shadings and different cosmic ionization rates of the disk, which drive the disk chemistry. The black cases show the final CO content for planetesimals forming at time 0 of the disk, effectively negating disk processes like chemical processing and radio transport of pebbles. The yellow cases show when planetesimals are formed, at 3 megayears instead, when such processes are given time to occur. This demonstrates that, first, the CO content of planetesimals is a strong function of the internal degassing rate, and second, that for varying formation times, distinct peaks can develop that display the radial variation due to disk chemistry. We stress that the disk model itself, meaning the disk size, mass, temperature, and other physical parameters remain identical, and all the variations seen in the plot comes from variations in degrees of disk processes and assumptions about the planetesimal formation process. Importantly, these results are in contrast to the situation described during the introduction, where the snowline location alone was responsible for the composition of solids and ices available for planet formation. This adds timing as a first-order parameter in planet composition.
These predictions therefore offer a way to test the level of geophysical processing of planetary building blocks on a system-wide level. Before speculating about planets though, we note that observations of second-generation gas in debris disks potentially offer a way to derive bulk CO and CO2 contents of planetesimals in such systems. Hence, the abundances in debris disks may give insights into the volatile chemistry that is set by disk and planetesimal evolution and can be compared to pristine solar system objects that could escape thermal processing. Our simulations in this context then suggest variations between planetary systems that should scale with the formation time of planetary bodies. Earlier formation of planetesimals means more processing, means lower volatile abundances. So if only a fraction of systems reach this efficient planetesimal processing stage, this would mean that statistically, the variance in carbon abundances across planetary systems should increase. Some systems may show very low abundances, while the not processed systems should resemble the chemistry set during the protoplanetary disk phase. Closer to home, apart from the more obvious comets and Kuiper belt objects, another potential testbed are these interstellar interlopers like Borisov, which seems to have inherited a highly CO-enriched composition. Further observations of more of these bodies may then yield another unique window into the compositions of planetary building blocks in extrasolar systems, and a new way to test some of the variations we've predicted in this work.
To summarize, we suggest that carbon abundances of planetary systems are globally influenced by disk chemistry and the geophysical evolution of planetary bodies after planetesimal formation. The inherited composition from the disk is set by gas and grain surface chemistry, pebble coagulation, and dynamics in the disk. Once planetesimals are formed, however, the local dust composition is altered by internal evolution due to heating from the interior of the body. Evidence from the solar system suggests that this heating is strongly time-dependent because of the short half-life of the most important radionuclide for heating, aluminum-26. The resulting degassing and devolatilization of planetesimals then crucially influences the volatile content that can be delivered to terrestrial worlds during the primary accretion phase and potentially during later accretion episodes due to dynamical mixing processes at later stages. The volatile precursor material that makes up the atmospheres and oceans of terrestrial planets in the inner disk in this scenario is a combination of the time evolution of disk chemistry and geophysical reset in growing planets. This presents an alternative to the standard scenario that is typically considered. Volatile and specifically carbon abundances are crucially influenced by the timing of planet formation. While we here focused on the highly volatile carbon and oxygen carriers, a substantial additional reservoir of carbon in the inner disk may be in refractory forms. Hence, future work will need to additionally take into account the processing of these more refractory forms of carbon. With this, I want to thank you for your attention. We would be most happy to receive your feedback or comments on our work.